Picking up where we left off on the previous video of Max Planck, we can simply just state that again the relationship E equals h nu, and these are quantities of energy. So again, we have Planck's constant, which is this very, very small number, times the frequency of the light itself, and then the multiple of this gives us an energy quantity. And again, we have certain quantities of this, so we would multiply that through. Let's get an example of how this would work. Light seems continuous. Just kind of stating this little fact here. Light seems continuous because h is very small. Here we go. Calculate. The energy of specifically yellow light. So this is an interesting kind of idea that yellow light has different amounts of energy in comparison to like blue or red. And we actually do know this. For example, if you go out in the sun, what are you most concerned about? Not necessarily by color, but sort of. The ultraviolet light, because it can give you like skin damage, a sunburn. So violet, ultraviolet, just outside the visible spectrum, has really high energy in comparison to violet or blue or specifically yellow. Well, let's take a look at a problem here. We'll set it up. E equals H, I want to set it up like this right now. HC lambda. Let me put it together a relationship. So this is the formula I'm going to use. Of course, I didn't tell us where this came from here. It actually comes from two different equations. So let's take a look here. C equals lambda nu. We see that. And then we have E equals H nu. Two different equations. If we combine these, so for example, if I solve this equation here for nu, swing H underneath here. Actually, let me change that. Instead of looking at this nu, we'll look at this nu. If I look at this nu and swing lambda under C, so in other words, I have, got nu is equal to C over lambda, and I put this in place, substituting in for this nu, that will give me these guys in place of nu, and you'll get this equation right here. So that's the one I'm going to be using. I would probably memorize this equation. You don't have to. Both of these are on your equation sheet that you would have for any quiz or test. It's just helpful. All right, let's take a look. If I plug in a couple numbers here that are known now, so here's my equation. E is what I'm solving for. H is a constant. So 6.626 times 10 to the negative 34 joules times seconds. And let's see, we have C. C is also a constant. So 3.0 times 10 to the 8th meters per second. So this second and this second are going to cancel each other out. And then on the bottom, I have nu. So I have to have something in meters. And as far as what I'm looking at here, I need to calculate the energy of yellow light. And something I didn't put in here, calculate the wavelength. Well, the wavelength of yellow light, I can look this up on some chart. The wavelength is going to be, for this particular example, with a wavelength of specifically, and again, it can vary a little bit. It doesn't have to be exactly this, but we're going to pick this wavelength. So 589 nanometers is what we're going to choose for this problem. All right, so if we plug this in, We don't have to think too hard, and we don't have to be exact with the proper scientific notation. We have this 589, and it's nanometers. Well, what are nanometers? It's times 10 to the negative 9. So again, we can move this around if it makes us feel more comfortable putting the point in here, but I'm just going to leave it as is. And notice again, meters and meters will cancel out, and we're going to have an answer that is only in joules, which is energy. That works out. If we plug all this in our calculator, being careful with the whole scientific notation stuff, everybody's holding on to one of these here, you will end up with an answer of 3.37 times 10 to the negative 19, which is very, very small, joules per photon. Every photon will have this amount of energy. Now, we may say, well, how much would it be a mole of photons? We could do that. We have this answer, and let's go ahead and incorporate that. 3.37 times 10 to the negative 19 joules per photon, and I'll go ahead and do it like this, so I can get the dimensional analysis thing going on. And then we multiply times Avogadro's number. So if I have per photon, and I want a mole, so how many photons are in a mole of photons? Well, just like any measurement, like a dozen, 6.02 times 10 to the 23rd photons are in 1 mole of photons. And that'll give us an answer of 2.03 times 10 to the 5th. So now it's a bigger number. Joules per mole of photons. There it is. That's the end of that one. Let's go ahead and do one more here. Just the idea. Radio stations. I don't know how much you guys listen to over-the-air radio stations, but there's 2 different types of bands on the radio. Over-the-air stuff. So 2 radio stations. One on the AM, one on the FM. On the AM dial, you have 1010. Let's go ahead and put a mark up here. On the AM dial, 1010. And the units they measure that are kilohertz, which is a frequency. Whoops. Frequency. Another station, this probably sounds maybe more familiar. Not any real stations, but we'll just using these. 98.3 megahertz. And again, if you look on your dial, you might actually see this on there. What we want to do is compare the energy. How much different are they? Well, obviously mega and kilo, we probably get a little bit of an idea how it's going to work. But let's incorporate that equation we used a little bit ago and see if we can make some sense of that. On the AM dial, we're going to use some of the numbers we have here. 6.626, we used this earlier. Very little energy, joules times seconds. And we're going to multiply that times the specific frequency that we have, which is 1010. Kilohertz, which again is waves per second. And if we punch this through on the calculator, we'll see that it's very low energy. Okay, well, the other one probably is too, but how do they compare? On the FM dial, same number, 6.626. Joules times seconds. And we'll do the whole 98.3. And these are megahertz. So mega is times 10 to the 6th. Again, waves per second. This time we get 6.51. But the number is times 10 to the negative 26th. So apparently this has 10 times more energy than these guys do. But they're both really, really low, which is why nobody's really concerned about getting bombarded with radio waves, because the energy that's hitting you is incredibly low, even though it's hitting you like all the time. We're not terribly concerned about it. Okay, end of lecture 2.